Hello everyone, all my dear students. Today we are going to see the new type of the flip-flop. Before this, here we had seen the various other types of flip-flops such as the SR flip-flop, or we can say the RS flip-flop by using the NOR gate. Then we had seen the NAND gate flip-flop. After that, to make the unique truth table of both the NAND gate flip-flop and the NOR gate flip-flop, we had seen the next version of that NAND gate flip-flop in which we apply the inverted inputs. So we had seen the clock RS flip-flop, and after that we had seen one different type of flip-flop, and that flip-flop is the D-type flip-flop. The D-type flip-flop is we also call as the data flip-flop or the delayed flip-flop. It provides some delay. Some means in minutes, in hours, no, in the microseconds it provides some delay. So that flip-flop is we also call as the delayed flip-flop. Okay, after this clock D-type flip-flop, we had seen one more version of that same D-type flip-flop, and that is we call as the age triggered D-type flip-flop. We had seen the concept of the age triggering, and then we had seen the age triggered D-type flip-flop. Okay, now it's time to learn the new type of the flip-flop, and that flip-flop is the JK flip-flop. Like the SR flip-flop, here the two inputs are there. In SR flip-flop, the two inputs are there, S input and the R input. Two outputs are there, Q and the Q bar. One thing we have to keep in mind, the flip-flop having the two outputs, these two outputs are always complement to each other. Now we have to see the next type of flip-flop, and that next type of flip-flop is we call JK flip-flop. In JK flip-flop, there are two inputs. One is the J input and other one is the K input. The J is equivalent to the S input and the K is equivalent to the R input. In this video lecture, we have to see how the JK flip-flop can be constructed and how the JK flip-flop works. Here first we draw the symbol of the JK flip-flop. The JK flip-flop's basic version we are going to see. For the clear concept, we are going to learn only the concept first and the basic concept, and then later on we will see its advanced version of the JK flip-flop. So to construct the JK flip-flop, here we do one change in the SR flip-flop. So for that, here first we draw the symbol of the SR flip-flop. Here is the SR flip-flop symbol. The two outputs are there, Q and the Q bar output. These two are the outputs. Now here the two inputs are there. Which are those inputs? The inputs are the S input and the R input. Two inputs are here, two outputs are here, and the two inputs are here. These two inputs are the S and the R input. Okay, now here we have to apply the input. So to apply the input, what we do here, we just add one AND gate at the upper side and one AND gate at the lower side. The one input here, that input is we call as the J input. Here it is the J input. This one is the J input, and here the second input lower side, that input is the K input. It means here this flip-flop is having the J input and the K input. Here it is the K input. Okay, now we have to apply the feedback, but opposite feedback we are going to apply. Application of feedback means just connecting the output to the input back. Okay, so here we apply the Q bar output to the upper gate and the Q output to the lower gate as a second input. So here I am going to apply the Q bar, and here at lower side we apply the Q. So here this is the Q bar and here the Q output. These two outputs are applied as a input back output back to the input. Okay, so this is the structure of the JK flip-flop, the normal JK flip-flop, not the clock JK flip-flop, only normal JK flip-flop. First we see the normal JK flip-flops operation, then later on we will see what happens if we apply the clock input. Okay, so here we consider the initial condition. Initially, suppose the flip-flop is in the set condition. The outputs in the set condition are Q equals to 1 and Q bar is equals to 0. Q equals to 1 and Q bar equals to 0. And now suppose we apply the input. J is equals to 0 and K is equals to 0. When J is equals to 0, K is equals to 0, it means here the output of the upper AND gate as well as the lower AND gate both are equals to 0, 0. Means here we get S is equals to 0 and R is also equals to 0. And as we know, the SR flip-flop goes into the no change condition. It remains in the no change condition when S input is equals to 0 and R input is also equals to 0. Means here the flip-flop was initially in the set condition. After application of the input J is equals to 0, K is equals to 0, we get the same state, means it remains in this set condition. Instead of this, we consider reset condition. Suppose here there is a reset condition of the flip-flop. The outputs are Q is equals to 0 and the Q bar is equals to 1. This is we call a reset condition. Again we apply the same input. J is equals to 0, K is equals to 0, as one input of upper and lower AND gate is low. It produces the low output, means once again we get S is equals to 0, R is equals to 0. So there is a reset condition producing the output Q is equals to 0 and Q bar is equals to 1. This is we call as a no change condition. It means when the J is equals to 0, K is equals to 0, here the Q is equals to what? Q is equals to the last state. Okay, so here the Q is equals to last state and the condition is we call as the no change condition. So we consider the next condition, and here the next condition is suppose J is equals to 0 and K is equals to 1. J is equals to 0, K is equals to 1, and now we consider the flip-flop is in this set condition. Flip-flop is in set condition, it means it produces the output Q is equals to 1 and Q bar is equals to 0. Q bar is applied as an input to the upper AND gate. So here one input of the upper AND gate, that is Q bar is equals to 0 and Q is applied as a one input to the lower AND gate. So Q is equals to 1. For the upper AND gate, one input is J is equals to 0. So we get here S is equals to 0. And for the lower AND gate, here the K is equals to 1 and the Q is equals to 1. So both inputs are 1, 1. It means R is equals to 1. Here the flip-flop produces the output, that outputs are the Q is equals to 0 and Q bar is equals to 1. This condition of the flip-flop is what we call it as a reset condition. We tabulate in the table where J is equals to 0, K is equals to 1, Q is equals to 0, and this condition is what we call it as a reset condition. Okay, now we consider the next condition where J is equals to 1 and K is equals to 0. Suppose J is equals to 1, K is equals to 0 and the flip-flop output state is in the reset state. So Q is equals to 0 and Q bar is equals to 1, or in other words we can say here when the J is equals to 1, K is equals to 0, depending on the previous state, here the output condition changes. Suppose here the flip-flop is in reset condition, means Q bar is equals to 1, which is applied to the upper AND gate. So here both the inputs are 1, 1. It means S is equals to 1. Now what is the input for the lower gate? the input for the lower gate is the K input and second input is the Q. So Q is equals to 0, Q equals to 0, K is equals to 0. It means we get here S is equals to 1, R is equals to 0. The flip-flop goes into the set condition and producing the output Q is equals to 1 and Q bar is equals to 0. Means when here J is equals to 1, K is equals to 0, Q is equals to 1, and this condition is what we call this condition as a set condition. Means here we get the set and the reset condition as per the set and the reset condition like the RS flip-flop or the D-type flip-flop. But what if both the inputs are 1, 1? Means when J is equals to 1, K is equals to 1. J is equals to 1 and K is equals to 1. Now the flip-flop is in the set condition. Suppose the flip-flop is in set condition. So here the Q is applied as an input to the lower gate. It means both the inputs of the lower AND gate are 1, 1. It means we get the output high, and this high output is applied to the R input. Okay. Now here for the upper AND gate, the inputs are J and the Q bar. Q bar is equals to 0 because in previous state the flip-flop was in the set condition. We considered the set condition. So Q bar is equals to 0. Q bar is applied as a 1 input to the upper gate. It means here this gate, the upper AND gate produces the low output, means S is equals to 0, R is equals to 1. And here due to this input condition, this flip-flop goes into the reset condition, producing the output Q is equals to 0 and Q bar is equals to 1. In previous flip-flop, in SR flip-flop, when S and the R input both are 1, 1, at that time there is a invalid condition, there is a raise condition, there is a forbidden condition. But in this flip-flop, instead of the forbidden condition, instead of the raise condition, invalid condition, we get the flip-flop in the reset condition. We tabulate it in a truth table. So when J is equals to 1, K is equals to 1, here what we got? We got here the reset condition, means Q is equals to 0. The name of this state we write down later on. Okay. Now the flip-flop is in reset condition. Again we apply the same input. J is equals to 1 and K is equals to 1. What if we apply the same input again? There is a different state of the flip-flop. But someone can say, sir, here there is a reset condition, so it remains in the reset condition, or there may be a raise condition. No, there is no raise condition. Here the condition occurred, that condition is different. Okay, so see how we get the different condition. Here the outputs Q and Q bar, that is Q equals to 0 and Q bar is equals to 1. Q is applied as input to the lower gate and Q bar is applied as input to the upper gate. So here the Q is equals to 0, it is applied to the lower gate. It means here the output of the lower gate which is applied as a R input to the flip-flop equals to 0. For upper S input, the AND gate having this upper AND gate having the J input which is equals to 1. Q bar is equals to 1, means both the inputs are 1, 1. Its output S is equals to what? It is equals to 1. Means S is equals to 1, R equals to 0. What we get? We get the flip-flop goes into the set condition, producing the output Q is equals to 1 and Q bar is equals to 0. So once again, when J is equals to 1, K is equals to 1, we get here the output, that output is equals to 1. Means we get the opposite state of the previous state. Previously here the outputs are Q equals to 0, Q bar is equals to 1. Now after application of the same input, J is equals to 1, K is equals to 1, we get the opposite output, means here the flip-flop was in the reset condition. Now it goes into the set condition. Here it was in the reset condition. Okay. Now if again we apply the same input, suppose J is 1, K is 1, the flip-flop is in the set condition. We see what happens now when the flip-flop is in the set condition. The Q is equals to 1. So Q is applied to the lower gate. Both the inputs are 1, 1. R is equals to 1. For upper AND gate, the inputs are Q bar and the J input. Q bar is equals to 0. So here one input of the upper AND gate is low. It produces the low output, means S is equals to 0. R is equals to 1. Now the flip-flop goes into the reset condition, producing the output Q is equals to 0 and Q bar is equals to 1. Here we get again when J is 1, K is 1, here the output is low, means here instead of writing this 0 and 1, we can directly write down here it is Q bar or Qn bar. Q bar means the output of the previous state, but it is in opposite output. Qn, what we use for the Qn, previous state, the Qn is the previous state of the flip-flop. So here opposite of the previous state of the flip-flop. Here again we get Qn bar and here again we get the Qn bar. But what is the name of this state? What is the name of this condition? The name of this condition is we call as the toggle condition. This condition is we call as a toggle condition, and due to this JK flip-flop is important than the RS flip-flop. Here this condition we can utilize, we can use this condition for the construction of the sequential logic circuit, and that sequential logic circuit is the counter circuit which counts the number of the clock pulses. Okay, so this is the JK flip-flop. There is no question on this JK flip-flop. The questions are always asked on the JK flip-flop with the clock. So the question is like this: draw the logic diagram of the clock JK flip-flop and explain its working. So we draw here the clock JK flip-flop, but we can say here we convert the normal flip-flop, normal JK flip-flop into the clock JK flip-flop. Okay, so to convert it into the clock JK flip-flop, what we do? We do a small change. And what is that change? As we had seen in the previous flip-flop, here in previous RS flip-flop, what we did? Just we applied the common clock input at both AND gates. So here that flip-flop is what we call that flip-flop is the clock JK flip-flop. But for this construction we required to use the 3-input AND gate instead of the 2-input AND gate. So here the third input we have to apply. The third input is the clock input. So here this input is we call the J input, and at lower side there is a K input. This one is the K input, and here the upper one input is the J input. One input of this upper AND gate and one input of the lower AND gate we tie together, we short together, and we apply a common input. That common input is the clock input, or that common input is the clock input, and we apply the input conditions. Now once again we consider when the clock is equals to 0. When the clock is equals to 0 means clock is low. This one time of the clock pulse, this time, from this time to here up to that time, here it is we call low time of the clock pulse, and this one is we call high time of the clock pulse. Okay, so we apply once the low time of the clock pulse, means clock pulse is having a binary value. That value is equals to 0. Whatever this J and K, either J is equals to 0 or k is equals to 0. If j is equals to 0, k equals to 0, again we get the same result. So we don't care about the j and k input here. That's why we make a cross in a truth table. We write down the cross in a truth table. So here when j is equals to 0, k equals to 0, or j is equals to 1, k equals to 1, but the clock pulse is equals to 0, it means the S input of this flip-flop is equals to 0 and the R input of the flip-flop is equals to 0. Why? Because the clock is applied to the AND gate, and we know that if any one input of the AND gate is low, then its output is low. So here the upper AND gate produces the low output as well as the lower AND gate produces the low output. So here we get S is equals to 0, R is equals to 0. It means here the flip-flop is in what? No change condition. Means we get here the no change condition. Now suppose here the clock pulse is high. The clock pulse is high means the high time period of the clock pulse means clock pulse is equals to 1. So we consider here the clock pulse is equals to 1. The clock pulse is equals to 1, but the j is equals to 0 and k is equals to 0. The clock pulse is equals to 1, but the j is 0 and the k is equals to 0. It means here again the output of this upper AND gate and the lower AND gate are low, means 0, 0. It means here S input is equals to 0, R input is equals to 0. Again we get the no change condition. Means when the clock pulse is low, whatever the value of the j and k input, we get the no change condition, as well as we get the no change condition if the clock pulse is high, but the j and k both inputs are low. J and k both inputs are 0, 0. So therefore here we get again the no change condition. Okay. So this is the first condition that we have to tabulate in the truth table. So here in truth table what we use? We use the various inputs. So what inputs are there? The inputs are the clock input CLK. Okay. Then J input, then the K input, and here the output we write down, that output is the Qn plus 1. You have to keep in mind the Qn and the Qn plus 1. Qn is the condition of the output condition of the flip-flop just before the clock goes high. Just before the clock goes high, and Qn plus 1 is the condition of the flip-flop just after the clock goes high. Means if you have to draw the conditions for these two, then here they just before, here at this particular point, here we get Qn and here this is the Qn plus 1. Okay. Qn plus 1 is the latest condition and Qn is the previous condition. Instead of this Qn plus 1, you can write down the Q only. Okay. So here we write down the Qn plus 1, and after that there is a condition of the flip-flop. Whatever the condition, either it is set condition, reset condition, whatever it is. So when the clock pulse is equals to 0, here j is equals to 0 or 1, we get here the last state, and last state is what? Last state is the Qn. Okay. And here we write down the condition as the no change condition. Next we write down here clock pulse is equals to 1, but the j is equals to 0 and k is equals to 0. What we get? We get again no change condition, means it remains in the previous state. So here it is NC, no change condition. Okay. Now we apply the input, that inputs are different than the 0 and 1. So here if the j is equals to 0 and the k is equals to 1, j is equals to 0, k is equals to 1, j is 0, k is equals to 1, it means here the output of this upper AND gate is equals to what? It is equals to 0. Why? Because here one input of this AND gate is low, therefore it is equals to 0. But to get the output state, we have to consider the previous state of the flip-flop. And what is that previous state? Suppose the flip-flop is in this set condition. Flip-flop is in this set condition. But why we are going to consider the previous condition? We are going to consider the previous condition because we applied the output back to the input. So we must know what is the previous output of the flip-flop. Okay. So here the flip-flop is in set condition. It means the Q is equals to what? Q is equals to 1 and Q is equals to 1 and Q bar is equals to 0. So Q is applied as a 1 input for the lower gate, means here we get Q is applied as a 1 input for the lower gate. So Q is equals to 1. For the lower gate, the J is equals to 1. Then the clock pulse is equals to 1 and the Q, which is the feedback to the input, that feedback is equals to 1. It means here R is equals to 1. For the upper gate, the Q bar is applied and Q bar is equals to 0. So therefore here the output of this upper AND gate is equals to 0. S is equals to 0. R is equals to 1. It means here the flip-flop goes into the reset condition. So here it produces the output Q is equals to 0 and Q bar is equals to 1. Means when the clock pulse is equals to 1, J is equals to 0, K is equals to 1 and here we get the flip-flop output Qn plus 1 is equals to 0 and this condition is what we call this condition as a reset condition. Okay, means we get the reset condition. Now suppose here the inputs are changed. The inputs are J is equals to 1 and K is equals to 0. J is equals to 1, K is equals to 0 and now the flip-flop is in the reset condition having the output Q is equals to 0 and Q is equals to 0 and Q bar is equals to 1. So Q is applied as an input to the lower AND gate, means here the output of this lower AND gate is equals to 0 and Q bar is applied as a 1 input to the upper AND gate. So upper AND gate inputs are Q bar is equals to 1, J is equals to 1 and this clock is equals to 1. So therefore here it produces the high output, means we get S is equals to 1, R is equals to 0, means the flip-flop goes into the set condition producing the output Q is equals to 1 and Q bar is equals to 0. So when the clock pulse is equals to 1, J is equals to 1, K is equals to 0, then Qn plus 1 is equals to 1 and this condition is what we call this condition as a set condition of the flip-flop. Now up to this point, this flip-flop works like the RS flip-flop. Okay, now we see what if the J is equals to 1, K is equals to 1 and clock pulse having high time period. The clock pulse having high time period means clock pulse is equals to 1. Now we have to consider only the output inputs. Suppose the feedback inputs, means suppose the flip-flop is in the set condition having the output Q is equals to 1, Q bar is equals to 0. So Q is equals to 1, this Q is applied as a 1 input for the lower AND gate and Q bar is applied as a 1 input for the upper AND gate, means here it is equals to 0 and the lower AND gate having the all inputs are 1, 1, 1. The clock is high, K is 1 and also Q is equals to 1. So we get here R is equals to 1 and here S is equals to 0 as one input of this upper AND gate is low. Okay, so S is equals to 0, R is equals to 1. The flip-flop produces the output Q is equals to 0 and Q bar is equals to 1. Why we get this type of output? Because of the toggle condition. Means when clock pulse is equals to 1, J is equals to 1, K is equals to 1. Here we get the output. That output is the Qn bar. Opposite state of the previous state. Means previously the flip-flop was in the set condition. Now what we got? Q is equals to 0. Q bar is equals to 1. It means this is the reset condition of the flip-flop. So here we write down the toggle condition. The condition is the toggle condition. T-O-G-G-L-E. Toggle condition. Now once again we consider what state we get when the flip-flop was previously in the reset condition. Means Q is equals to 0, Q bar is equals to 1. Once again, J is equals to 1, K is equals to 1. And this clock pulse is equals to 1, means clock pulse having its high time. Okay. So, J is 1, K is 1, means two inputs of this upper AND gate are 1, 1. And third input is the Q bar. So, Q bar is also equals to 1. Lower side, here one input is the clock is equals to 1, second input is K is equals to 1, and third input is the Q is feedback. So Q is equals to 0, means the output of this lower gate is equals to 0 and output of this upper AND gate is equals to 1. It means input to the flip-flop S is equals to 1, R is equals to 0. So here this flip-flop goes into the set condition, producing the output Q is equals to 1 and Q bar is equals to 0. So clock is equals to 1, J is equals to 1, K is equals to 1. We get here the previous state of the flip-flop, opposite state of the previous state. So previous state is the reset condition. Now we get it is a set condition. So we write down here Qn bar, and this condition is what we call, this condition is we call as the toggle condition. Okay. So this is the clock JK flip-flop. The clock JK flip-flop is now constructed by using this symbolical representation. We require to draw its logic diagram, but we will see the logic diagram by using the NAND gate. So in next video lecture, we will see the construction of the clock JK flip-flop by using the NAND gate, and then we will see the advantage of this clock JK flip-flop and the disadvantage of the clock JK flip-flop. So if you understood this video lecture, the clock JK flip-flop, then hit the like button, subscribe the channel and share with your friends. Thanks for watching the video. Take care.